I see a lot of people figured out to come early, so good for you. So as you recall, my name is Randy Bryant, and I'm co-instructor of this course along with Dave O'Halloran. And for the next couple lectures, the first part of this course really, we'll be talking about sort of data representations, in particular how numbers are represented in different forms and some of the properties. And you saw in that when I talked last week, I showed you things like you can multiply some numbers together that are positive and get negative results. So what we want to understand is what is the bit level representation of numbers and how does that affect some of the properties you have when you operate them on, and especially looking at the corner cases when things overflow or sort of don't do what you might expect them to do. So we'll start off with very basic stuff of how numbers are represented, especially integer valued numbers are represented in bits. So I think you've pretty well figured out in this world that the whole digital world is sort of based on binary values. And that wasn't always the case. I mean, since humans have 10 fingers and 10 toes, a lot of the world was based on the decimal system. And it was really only, and in fact, the first electronic computer, the ENIAC, built in University of Pennsylvania, basically did all of its arithmetic using base 10. They had 10 vacuum tubes per digit they wanted to represent. So they basically turned on or off those tubes to represent which of the 10 possible digits you could want. And it really didn't come to people until later than that, so that's 1948, that they really should just think about base 2 for everything. And the reason why bits are great is in the digital world, you can sort of take what's otherwise an analog signal and quantify it and just say, I'm going to say that one range of values, let's say it's a low voltage, I'm going to call that a 0. And a high range of values, I'm going to call it a 1. And if there's noise or imperfections in the circuit or anything going on, as long as that doesn't exceed these thresholds you've set up, then you'll get a nice clean signal out of it. And that's the main advantage of digital processing over analog processing. And so that's sort of at the core why everything we do, and especially for storing information, it turns out it's much easier to store one bit of information or a digital value than it is to store an analog value. And sorry, this kind of slides went a little crazy on animations. So the point is that we represent all the numbers in a computer as sets of bits, and I think you generally understand that fairly well. And so of course the familiar binary representation of integers, which we'll go over today, just uses a bit position for each power of 2. We can also represent values that are fractional, and we'll talk about that a week from today when we do floating point numbers, where what you do is to the right of the binary point, so this is no longer a decimal point, it's a binary point. And so something to the left of that would have weight 2 to the 0, and the next one over would have weight 2 to the 1. But what you do is as you go to the right, that has weight 2 to the minus 1 to the minus 2. In other words, this is 1, this is 2, this is 1/2, and this is 1/4. So we can represent, just like you do the decimal representation of fractions, we can do the binary representation of fractions. And that's the core of floating point number representations. And so it gets very annoying if you have, say, 32 or even 64-bit numbers to be writing these strings of ones and zeros out. And so what we use, and what's become largely the most common, is to group collections of 4 bits at a time into, and then represent that in base 16, or what's known as hexadecimal representation, using the letters A through F as values 10 through 15. And you'll spend a lot of time staring at hexadecimal numbers this year. And you'll get pretty good at being able to look at a hex number and just write it out in binary. The way I do it, just to tell you, is I've got the values from 0 to 9 wired down pretty well. And then I keep track of a few special cases. 1, 0, 1, 0 is A. 1, 1, 0, 0 is C. And 1, 1, 1, 1 is F. And for B, D, and E, I kind of interpolate between those. So if you want to develop that skill, that's the way you can do it. You're looking for something.
Is there an HDMI connector that we forgot here?
An HDMI to what? No, I don't think there's any connector here.
No?
No.
All right, thank you.
So that's something you're going to end up wanting to be able to do. So in C, we don't, in most declarations, you don't actually are told exactly how many bytes. A byte is 8 bits. Each data value is represented as. And that's partly C was designed actually back when microprocessors only had 16-bit words. It was actually before microprocessors. So 16-bit words were a fairly standard thing. And over time, that's expanded from 16 to 32 to now 64. And so C, rather than sort of in advance saying, here's how many bytes every value will have, has these slightly ambiguous terms that vary actually from one machine to the next. And if you're a very careful C programmer, you have to anticipate that some. But what we'll deal with is x86-64 is the class of machines we'll be working with exclusively this term. And so you can see that when you declare something to be a char, sometimes people call that a char, that's a 1-byte value. A short is 16 bits. An int is 32. And if you want to get all 64 bits, you have to declare it to be a long. And then, again, there's two different precisions of floating point. There's 4-byte or 32-bit floating point numbers and 64-bit. There's also a slightly obscure holdover from ancient days of floating point, where there's a special representation in Intel machines that uses a 10-byte or 80-bit representation. And when you use that on a 64-bit machine, they sort of waste an extra 6 bytes out of that so that everything is aligned in 16-byte increments. The other thing, and this is an important feature, is any address is defined to be the sort of the word size of the machine. When they say it's a 64-bit machine, what they really mean is that the addresses are 64-bit values or 8-byte values. And that's different, for example, if you use an older machine, a 32-bit machine, those will only be 32-bit addresses. So the basis then, and I imagine you've had this at some point, of how do we then think about bits is based on Boolean algebra, which has actually comes from the 1890s, that a guy named George Boole, who recognized a sort of relation between what we'd call bits, but they weren't called bits back then, 0, 1, and logic, or basically truth values and logic. Thinking of an algebra, sort of a structured set of operations you could apply that would capture some of the concepts that people assume in logic. So for example, if we think of 1 being true and 0 being false, then the AND operation is true if both of the inputs, both of the arguments are true. So we get this chart here. And similarly, the OR operation is true if either input is true or 1. The NOT is just to flip the bit. And then the exclusive OR is what you get when you say it's one or the other but not both. And so it has this representation. So just as a bit of history, it was a master's degree student at MIT named Claude Shannon who had taken a course in logic as an undergraduate at University of Michigan. And he was the one who made the connection between thinking about this what was at the time very obscure branch of something or other of logic and applying it to digital systems back in an era when they actually built these things out of electromechanical relays. And so his master's thesis is probably the most impactful master's thesis in the history of humankind. And you always wonder, well, what did they do before that then? You know, how did they even think about these things? So anyways, the idea of applying this algebra then to bits is not something that's sort of been true since the world began. It's something that's a relatively modern concept. Now, what's an important thing that might be less obvious is we can also do these over words. We can do these Boolean operations where we apply them on each successive bit in that word. And these symbols we use, the ampersand, vertical bar, caret, and tilde, are actually the ones that C uses to represent these operations. And so, again, if we look at here, the 1 is only if both of the values are 1. And for the one, or it's if either of them are 1. The exclusive or if one is 1 and the other is 0. And tilde is just to invert the bits of it. So again, we will spend a lot of time making use of the fact that in C, and this is one of the features of C that people like, is that you can do these sort of very low-level bit manipulations directly in the language. And this actually turns out to be useful in practice, and it's sort of implicit of a way of representing sets of values. So this example is imagine we want to represent sets where the elements of the set are numbers ranging between 0 and 7. So 1 byte is enough to capture 8 cases. And we'll just, if we number the bits, and we number them from right to left, so this is bit 0, so that would represent whether or not the value 0 is an element of the set. And similarly here you'll see 0, 1, 2, 3. So we're saying that bit 3 being 1 here means 3 is an element of the set, and so forth. And so the idea is then the AND operation becomes like set intersection, the OR operation becomes like set union, and the exclusive OR operation is what's called symmetric difference. And so these are actually, and tilde is like set complement. So these are actually very common. For example, there's operations you'll learn later when we look at file I/O, about I/O, that you can track. I want to know which set of possible inputs to the system, think of different network connections, have an input ready for me to read. And there's a data structure that it's sort of hidden away among some C library calls, but it basically is using exactly this representation, about 1,000 bits worth of information to represent these sets and do manipulation on those sets. So this is a very common and widely used representation of sets in computer science. So as I mentioned, those are available directly in C, the ampersand, vertical bar, tilde, and caret. One thing that's really, really important, and that programmers screw it up all the time, beginning programmers a lot, and even experienced programmers from time to time, is to mix up the single ampersand and the double ampersand, or the single vertical bar and the double vertical bar, and the tilde versus the exclamation mark, which is often pronounced bang. So, and the reason, so obviously there's sort of a syntactic similarity, and there's actually somewhat of a semantic relation too, that this is another kind of and, another kind of or, and another kind of not. But if you mix and match these, you're certainly going to have problems. So the double bar ones aren't thinking about bitwise operations. They're thinking about something that's either true or false, period. And in that representation, the number 0 is the thing that's false, and anything else, any other bit pattern, is considered to be true. And so the other feature that the double bar, operations give you is what's called early termination. So in particular, if we do some examples on some hex pattern 4-1, so this is not a 0, and so that's considered true in this interpretation, and so the bang of that, the not of that, is 0. And similarly, if you have 0, the not of that is 1. And if you apply bang to a number twice, you'll get back a 1 unless it was 0. And then similarly, these patterns here are, the reason why this returns 1 is because it's considered 2 cases that are true. So it's not doing bitwise operations. It's just trying to create true and false. It's interpreting arguments to be either true or false and returning either true or false. But when it returns true, it returns 1 and not whatever number you happen to give it. So obviously, this is a very different operations than you have with the single versions of those. And, but it's easy just because you mentally slip or because you type something wrong to do the wrong thing. But in particular, this early termination is something that, of course, people use a lot. If you want to make sure that you're not accessing a null pointer, you can test whether that's a null pointer first before accessing it. And this, if this is 0 or null, then it won't do the dereferencing of null. So it's a fairly useful feature as well. So anyways, just that's an aside. At this level, we're mostly looking at bits, but just as a programming note, don't mix these up. The other class of operations we'll make use of a lot are shifting, which again is not something that you normally sort of as beginning programmers think about too much. And there's a curious feature that left shifts are always the same, but there's 2 different flavors of right shift. And we'll see in a little bit later why there's 2 different flavors of right shift. But the idea then of shifting is that you have some argument x, and you want to shift it some number of positions, either to the left or to the right, given by y. And so when you shift left, you just fill in whatever value there was. So you pick up the, I'm shifting by 3, so I'll take the low order 5 bits, move them over 3 positions, and then fill in with a 0. And whatever was in the upper positions of that original word, they just sort of disappear into nowhere. Similarly, if I do a right shift, I take the upper 6 bits, I move them over 2 positions, and I fill in with zeros. So that's a logical shift, and that's, well, it's logical. There's another flavor called the arithmetic shift, which it differs in that the rule for what bits you fill in with are not based on the, are not zeros necessarily, but it's whatever the most significant bit was in the original value. So it doesn't matter here because the most significant bit was 0. But you'll see in the case here of where the leading bit was a 1, that when I shift it to the right arithmetically, I'll fill it in with 1s. And that'll make sense more when we understand how negative numbers get represented in a machine. And that's the purpose of it and why it's called arithmetic. The other thing that is kind of confusing to people is what should happen if you say, I want to shift an 8-bit number 8 positions to the left. And x is a single byte. what do you think you should get? 0? That would be a pretty logical thing. You kind of shift all those bits out, you fill them with zeros. On most machines, you'll get whatever x was. Because what it will do is it will compute this number mod 8. And the reason that happens is, if you think about it, it's looking at just the low order 3 bits of the shift amount and ignoring all the rest. So that's effectively like modulo 8. So that's just a warning. And on some machines, it does what you just thought it should. And other machines, it does this. And so there's no guarantee in C that it will be one way or the other. Same with if you try to shift left by a negative number, that might be logically, well, I guess you really want to shift right then, but that usually doesn't work either. So now let's talk about number representations. And this is sort of a very core idea that you have to really have wired in you. And I'm going to illustrate it with some examples. So these two equations then are everything that we'll talk about sort of stems from them. So one is if you have an unsigned number, then basically, it keeps jumping on me. If you have an unsigned number, then this is just the conversion. Then BTU means from bits, a bit level representation, to an unsigned number of some bit pattern. It just says, we'll just add up the sum of the weighted bits, where each bit is weighted by a power of 2. And the only difference when we look at 2's complement, which is a way to represent both negative and positive numbers, is we'll consider the most significant bit to be what's called the sign bit. So it will have a negative value. So let me just illustrate this with, I'll use some running examples. And we'll just use 5-bit numbers just as a way. It really helps often if you're trying to understand this stuff to do it for some smaller cases. So if we think about bit positions, um, 0 through 4, then those represent different powers of 2, weights, as I've shown. And so now if we take some bit pattern, like so that's what I'll call x. And I want to convert that to an unsigned number, I will just combine 8 plus 4 plus 1, and I'll get 13. Right? So that's all that equation says, the left-hand equation. Just take the bit positions that are 1s, use the corresponding power of 2, and you're done. And similarly, if I have a number where there's a leading bit, it will be 16 plus 4 plus 2, so that will be 22. And so that's the unsigned case. And the signed case is the same idea, except that most significant bit has a negative value. So it will still, this is I. And our weights will be 1, 2, 4, 8. But this will now be minus 16. So that's what the equation on the right is saying. That this bit, now we're going to change it from being a negative number to a positive. So obviously, if I have this as my bit pattern, it's going to be the same because the other bits stay the same. So let's do it for this case of 1, 0, 1, 1, 0. So that will be minus 16 plus 4 plus 2. So that will equal minus 10. Right? So you see, in this case, we have the same bit pattern. It's just, if we interpret it, how we think about what number this represents, then in one case it's a positive number, 22, and in another case it's a negative number, minus 10. And that's what these equations are saying. And so the most significant bit is sometimes called the sign bit, because if it's a 1, the number is going to be negative. So let's sort of think about what are the sort of extreme ranges of numbers we can get with these two different representations. So obviously, if these are all zeros, my number is going to equal 0. And if it's all 1, it'll be 16 plus 8 plus 4 plus 2 plus 1 will be 31. And over here, for the 2's complement, the smallest number, well, the largest number will actually be, let me do it this way. Actually, the most negative number, so the smallest number in the strictest sense of the word, is this. It's minus 16. Right, and you can argue this, by the way, that this is the only bit that has a negative weight. All the other ones have positive ones. So certainly 1 and all the rest being zeros is going to be the smallest number. And similarly, the largest number you can represent will be 8 plus 4 plus 2 plus 1, which is 15. And so we call this number U max. And we call this number T max. And we call this number T min. So there's a few things to observe about these numbers. That, remember, this is a 5-bit word size, right? So you'll see that 31 is pretty close to 32, right? In fact, it's 2 to the 5th minus 1. And in general, if it's a 5, and that's for a 5-bit word size, so you would say in general it will have value 2 to the W if I have a W bit number minus 1. And that's what this shows. And similarly over here, this is 2 to the minus 2 to the 4th. And so we'd say in general that will be minus 2 to the W if it's a W bit number minus 1. Right, and all these make sense. By the way, you'll notice one other feature is a whole string of 1s like this. If you sum up those digits, 8 plus 4 plus 2 plus 1 will be 1 less than the next bit position up. And you can think about that if you were to count this number. If you were to increment this number by 1, you'd get 1, 1 is 0, carry 1, and so forth, and you'd carry that value up to this position. So there's various ways you can think about that. And then similarly, this number is 2 to the 4th minus 1. And so that's equal to 2 to the W minus 1 minus 1. As is shown here. So there's a lot of, the book goes through formulas and does derivations, but if you just think about it in these smaller scale ways, the intuition is pretty easy to get. And don't get lost in formulas when really at the gut level it's a fairly straightforward set of ideas. Or if you ever see some equations and you're confused, try out some small examples and see what they're saying. Another interesting number in the world of 2's complement is what happens when you have all ones in your bit pattern. And that will have minus 16 plus 8 plus 4 plus 2 plus 1. And that will equal minus 1. So the bit pattern, all ones, is always a minus 1 in this representation. I should mention 2's complement is not the only way to represent positive and negative numbers, what's sometimes called sign numbers. But it's so universal that you'll hardly ever encounter another case. So if you understand 2's complement, you have a pretty good understanding of what really is going on. So these numbers I call U max, the biggest unsigned number, T min, the smallest, most negative 2's complement number, and T max, the largest, most positive 2's complement. This chart shows the range of values for different word sizes, or different numbers of bytes. And so you'll see that with an 8-bit number, you only have 256 possibilities, right? And so we can either choose to think of those as representing the range from 0 to 255, or basically with 2's complement numbers, we're just doing a sort of a wraparound. We're saying, well, we're going to have half of them be negative, and the other half will be either 0 or positive. And so it's a pretty limited range of values, of course. And then 16, and believe me, back when computers had 16-bit word sizes, it was a nuisance to keep your numbers within that range. And 32 gives you a pretty decent range. It used to be said Microsoft had to go to 64-bit word size to represent Bill Gates' net worth. But for me, at least, this would easily handle my range of normal day-to-day transactions. So, but now with 64 bits, at least to us nowadays, those seem like really big numbers, and hard to imagine exceeding the bounds of those. So one interesting feature that you noticed here was I was like this case here. And this case here. Excuse me. And then this case here of all ones, I was comparing it to this case here of all ones. So in other words, in both these cases, and it's a little hard to jump boards here, you're seeing that you have the same bit pattern in either case, but they represent different numeric values, because one is a 2's complement case and the other is an unsigned, right? And you can actually see the relation between them is pretty simple, because basically what we're doing is we're jumping between a plus 16 and a minus 16 between those. And so you'd expect it to change by 32, right? And you see that here, that this is 31 here and minus 1. This is 22 and minus 10. So they differ from each other by plus or minus 32. 2 to the fifth, 2 to the word size. And so there's sort of a long derivation in the book and things here, but that connection is actually fairly important. because when you jump back and forth between unsigned numbers and 2's complement numbers in C, that's the jump that you get. In other words, when and so you'll often find cases where what used to be a very large number because it was unsigned all of a sudden becomes a negative number because it's considered 2's complement. So that's what this next part covers. We'll say that if we take a chart of 4-bit numbers and we write out all the possible values as unsigned or as 2's complement numbers, then the ones where the higher order bit is 0 will be the same in both cases. The ones where the higher order bit is a 1, in this case will differ by 16, 2 to the 4th. And similarly, you'll notice that these numbers, there's a unique, it goes unique in both directions. For any given bit pattern, there's a unique number it represents. And similarly, for any number within the given range, there's a unique bit pattern. So we can sort of jump between those two and say, I can make up a rule for converting between a 2's complement number x and an unsigned number ux that basically says I'll use the same bits, I'll just think of them as being different numbers. And so, and you can go either way. So for example, if we thought of this as a 2's complement representation, it's -1. This function I'm calling t to u goes from that number -1 to this number 31 as where in between the two I'm saying they both have the same bit pattern. And the reason why this rather function that would otherwise seem to have no particular use is important is because that's basically what happens in C, or actually in the program. The program on the computer itself has no clue whether a given bit pattern, if it's something you're thinking of as being a negative unsigned number or 2's complement number, it's just a bunch of bits to it. And similarly, we can go back and forth between 2's complement and unsigned, keeping the bit patterns the same. And so I'll call that t to u when I go from signed to unsigned, 2's complement to unsigned. And similarly, I'll call it u to t if I go from unsigned to signed. And as I mentioned, the difference for the numbers where the higher order bit is a 1 will be by a factor 2 to the w, where w is the word size of the word. And so this can be thought of as a function where let me just draw it out. Over here with my 5-bit numbers, that is the number, this is 2's complement again, so that was the number -16. And then there'll be some other negative numbers up to all 1s. This number -1. And then I'll have 0. And so forth. And then all up to, oops, I'm going to run out of room. Plus 15, right? Just realized I got myself in trouble. Blackboard management is, they didn't teach me this in school. So I'm going to use 2 boards at once here. Okay. Let me set this up. Okay. We'll make it work. So now, when we go from the t to u function, then, these numbers are going to just carry over. We'll get 0 up through 15. But now this number here will become positive 16. And all ones will become positive 31. Right? And so that's what this picture is showing, is that for the pink numbers are the ones that flip between negative and actually the largest of the positive numbers. And then the green numbers are the ones that stay the same because their leading bits are zeros. So why does this matter? You never saw it if you programmed in Python, say, or even Java. You don't see that. And the reason is because C is one of the few languages where unsigned is actually an explicit data type. And so you can declare a value being unsigned, and it's if you just say unsigned, what you're really saying is unsigned int. Or you can call something an unsigned char, an unsigned short, or an unsigned long. So, and you're declaring in C that it should think about using this representation we show on the right when it's working on those numbers. So that's sort of one thing. And it's one thing if you declare a number and use it that way, but what gets people, and often got you, is if you declare something, if you have, in this case, something that's declared as a 2's complement number x, tx, and you assign it a value u at y, x, it'll do an implicit casting, which is exactly based on this conversion that we've been talking about, and vice versa. And so as this example goes through, this goes through some examples that if I look at two numbers and I compare them, or actually I do any operation on them, I add them, divide them, anything, implicitly it will try to make these two be of the same type. And the way it will do that is to say if both of them are signed, then I'll treat them as a signed case. If either of them is unsigned, then I'll convert the other one to be an unsigned number and do the operation. And so, in particular, this set of examples is, imagine I'm comparing these. I'm saying these numbers are either equal, less, or greater. What will the outcomes be? And the key to answering that question is to first of all figure out, okay, is it a signed or an unsigned comparison? Should I convert one of these numbers to either of these numbers to an unsigned form before I do it? And the rule is, if either argument is unsigned, then you got to do it. And as you see, when you put a u at the end, either a lowercase u or an uppercase u at the end of a numeric constant, you're saying this is an unsigned value. So, for example, if we compare 0 and 0 unsigned, they're equal. And if we combine -1, compare -1 to 0, we'll get that the first one is less, because -1 is less than 0. But what would happen with the next one when we compare -1 to an unsigned 0? Greater. Right. So this is the surprise. And it has to do with a number that I erased. But we can still get it. Remember, this is -1. But when I cast that to an unsigned number, I'm flipping this from -16 to +16 and turning this into 31. I'm turning it into actually the largest number I can represent. And so it will be greater than 0. So it's a little bit weird to think about. I took an unsigned 0, which after all is just 0, and compared it to a -1, and it said, oh, you really meant 31, didn't you? Or whatever word size we're using. And so it said it's greater. And basically the rest of these you can answer in a similar way. That these two numbers are, this is clearly one smaller than this. No, I'm sorry. This is a positive number, this is a negative number, and I compare those, and the positive will be greater than the negative. I'll tell you in a minute why this number is written this way. The next one, it's the same pair of numbers, but you see it's flipped. And the reason is that this number on the left is T max for so it's the bit pattern in a 32-bit number. And to this day, I have not memorized this number, by the way. But, and then this number is actually T min. And that when I subtract, you can think of it as this is negative T max minus 1, so that's T min. So if I do an unsigned comparison between those two, now think of those, this leading bit not being a negative weight but a positive weight, you'll see that this is a bigger number than this one. And so it goes that minus 1 is greater than minus 2 if they're unsigned, because minus 1 is, you can think of it as converts into U max. It'll be the biggest number possible. And minus 2 will be, would be 1, 1, 1, 1, 0. So that can get fairly confusing. One final quirk, this way of writing this number is, there's a little aside in the book about it. If you write this number as you'd expect to, as minus blah, 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 648, it will actually get, the C compiler gets kind of confused by that for obscure reasons. One other thing I should point out that it's a property that I don't think we cover well enough here. Well, let me see. There's a few things that the slides don't really cover here, and I don't know why not. I like to point out. That are kind of useful properties to keep track of. Is that you notice that if you look at the absolute value of T max and you compare it to the absolute value of T min, that it's off by 1. Right? So that the negative number is more negative, the smallest negative number is more negative than the largest positive number is positive. And the reason for that actually is fairly simple if you think about it, is that the cases where you have zeros include the number 0. So you can see it better. And there's 2 to the half year range is occupied by those numbers. And the negative numbers are all negative. And so the other half of the range is in there. And the point is that you had to use one of these for 0. And so there's one less value left over. And that's why you end up with this sort of asymmetry. And this asymmetry is the cause of no end of pain in various ways. That, like if you, the classic example is if you implement absolute value, like so, what does this return for t min? Yeah? It returns t min. We'll talk a little bit. Basically, when you try to negate this number that's here, you'll end up with it back again. So it's always a corner case. And whenever we do program testing, we always throw that case in there to break things. Question?
When you said, well, that case you said earlier about, I forget the big number, but how you had to write it as negative something something minus 1?
Yes.
Is that the number itself?
Mm-hmm.
Does that mess up? Does that like create some weird bugs or anything?
No. They do that. If you ever look at the in the C constants, they use this as a way of representing t min. And they do it for that reason, because you see, it's exactly this and they put parentheses around it, so there's no precedence problem. But you see that number that ends 647, that's t max. And so basically, it's just saying that t min is minus t max minus 1. Question?
Do those rules also apply for arithmetic operations? So for example, if you did unsigned 0 plus -1, you would get u max?
Yeah.
Yeah.
Mm-hmm. Yes. So comparison is just a special case of the more general one, which is addition, subtraction, all of those. If either argument is unsigned, then it interprets the remaining one as being unsigned. It turns out, and we'll get into this more next time as far as bit patterns, but it turns out that at the bit level, addition, subtraction, even multiplication are the same whether it's an unsigned number or a 2's complement number. So we'll talk about that more next time. And the other thing to observe, sort of property, is you saw that U max is sort of like twice T max plus 1. Right? So before U max was 15 in our 5-bit numbers. And that's, again, not too hard to figure out. Here's one way to think about it. T max is a 0 followed by a bunch of 1s. And if I want to double that number, I basically shift it left by 1 position. And that would end up with a 0 here. So this is t max. And this is twice t max. And now if I add a 1 to that, I'll just set this bit to 1 and get this. So there's various ways you can think about it, but that's one way to do it. There's one other thing that I wanted to mention too. This can get you into a lot of trouble programming wise. So let me just show you what I mean. So imagine I wanted to go backwards through an array. So I write a loop of the form for I equals n minus 1, I is greater than or equal to 0, I minus minus, and then I do something with array element a of I. I'll just call some function I. Whatever you want to do in that loop. So that's a pretty standard pattern in a loop, right? Except that you write this greater equal to 1, 0. I mean, you can imagine various uses for that. So here's an interesting question. What if I were declared as being unsigned? Because it's array index after all. What will happen with this loop? Yeah? What's that? Yes. So the loop will go forever. What would most likely happen is I would go from being 0 to being u max. And that's a really big number. And the array, you'd most likely cause a memory fault because it's so far out of bounds. But the point is it wouldn't do what you want. It wouldn't stop where you want it to. And because of the simple reason that I is, of course, I is always going to be greater or equal to 0 because it's an unsigned number. So that's one you'd say, OK, well, you should have figured that one out. It can be more subtle, though. If you have something like int I, and then we say something like, let me just change it here a little bit. So this will be, something like this where I'm mixing metaphors here, I have to confess. But if you use the standard term size of, which is the way you get how many bytes it takes to represent some given data type, so this will actually be the number 1. So it's not the same loop as before, but imagine I'm sort of mixing in my arithmetic and making use of some of these built-in forms. What would happen with this loop? Yes?
I think size of returns an unsigned.
Right.
That it would then convert it to an unsigned.
Yes, exactly. So size of returns an unsigned value. It's not actually a function, it's a built-in, but it's the result of size of is considered to be unsigned. And so just like I was saying, if you have a signed value and an unsigned in any kind of arithmetic, it'll treat the combination of the two as unsigned. And so it will actually do an unsigned comparison here, which is almost surely not what you wanted. And this will just, you'll look at this program and you won't have any idea why it's crashing. You'll be so confused. And that's the kind of thing you have to know. It's one of the quirks of C that probably if they could start over again and redesign it, they'd come up with some different set of conventions than they did. But unfortunately, it's way too late for that. So this is just one of those things you have to remember. But yes, my point is there's some subtleties in C about this business of signed versus unsigned arithmetic. Okay, so now let's look at a sort of final class of operations, which is, suppose I have a number that's so many bits, say 8 bits, and I want to now expand it to be a 16-bit number. There's a fairly cute rule for doing this that's called sign extension. I'm talking about 2's complement numbers here, of how you go take a number and make it bigger without changing its value. And the basic rule is you do it by copying the sign bit to the left. So let me give you the intuition behind that. So let's look at some 4-bit values. Well, it's pretty straightforward. If the leading bit is a 0, I'm just going to do a left shift and then fill in. So right. Wait, what am I talking about? I got ahead of myself. I'm talking about something totally different. No, sorry. The same number. I'm not changing the number. I'm keeping it the same. So I just add a 0 to the lead, and this will be the number 6 still. This is plus 4 plus 2 equals 6. But now let's think about it as where there's a leading sign bit. So this is minus 8 plus 4 plus 2 is equal to minus 2. So now look at what happens if I copy that sign bit over one position. So this becomes a 1, 1, 1, 1, 0. And what happens is this is now has value plus 8 here, but the sign bit has value minus 16. And then this is still plus 2 and plus 4. And so it will still equal minus 2. So here's what happened. Before my sign bit had a weight of minus 8, and my new sign bit has a weight of minus 16, but I converted that old sign bit into a positive number, which is plus 8, and those two canceled out, so, right? You combine those two and you get minus 8, which is exactly this. So you see, by sort of copying that sign bit over, giving it twice the weight, turning it what was the sign bit into a positive number, you don't change the net effect of the sum. And that's exactly the idea of sign extension. Just keep going with that as far as you need to carry it over. And each time you're doing it, you're effectively doing this business of coming up with a pair of bits that end up with the same value as this original bit. So that's the idea of sign extension. And you'll see that a lot in bit patterns, especially if you see a bit pattern that starts with a bunch of F's. What that tells you, remember F is just 4 ones. Is a whole bunch of leading ones. That tells you the number is negative. Negative, but not too far away from 0, right? And you'll see that over and over again. You'll see bit patterns, and you just sort of want to, when you see leading Fs, you say, oh, that's a negative number. I know what's going on there. And so here's some examples, but like you can see, the main idea is you carry that leading bit from the 16-bit case over and make as many copies as you need to expand the word size. And I should mention, with the unsigned case, obviously you just want to fill in with zeros. Do we talk about truncation? It's sort of missing slides in this, but a final case to look at is what happens if I make something shorter. So if I had my unsigned number from before, if this were an unsigned number, this would be 1, 2, 8, 16, 14, 17, right? What if I decided, oh, I can't afford 4 bit. I don't have enough money for 5 bits. I'm only going to give you 4. Well, you basically just drop the most significant bit. And you get 8 plus 2 plus 1, which is 11, which is 9. And the relation there is that this is, it's like modular arithmetic. Right? Mod 16. You're taking, no? Thank you. It's the risk of improvising. So 27. And 11. Yeah, that makes sense. Difference is 16. I knew that. Okay, excuse me for my stumbling, but the point being that when you drop this thing, effectively you're just taking the mod some power of 2 of it. Like I mentioned the case where you're taking modulo 8. If you just keep only the lowest order 3 bits, you're having a modulo 8. Now this is sort of logical in the unsigned world. You know, modular arithmetic is something that was understood by the ancient Greeks. So not too far away from human experience. But it gets a little bit funky if you're dealing with 2's complement numbers, because this is now 10, 11, minus 5, right? But this number, if I just drop this bit and call it a 4-bit number, this now becomes minus 8, 2, and 1. Which is minus 5. You say, how'd that happen? Well, actually, if you look at it, this is just what you'd get by sign extension, right? So this wasn't a very interesting example. But if we changed it to this, then this would be minus 13, and this would be plus 3. And it's a little harder to think about in terms of modular arithmetic. The way you basically have to think about it is, well, you know, this is minus 13, but it's really kind of like 27, and 27 mod 16 is sort of like, well, or no, this isn't 20. We changed our number, right? So this is really kind of like 19, and 19 mod 16 is 3, and this is 3. So you can sort of do it by coming back around to it, but it's not some arithmetic property that would jump out at you as being something logical. But that happens all the time, and it's very common for numbers to get truncated for one reason or another. And you can see that you can have a negative number become a positive number. You can have a positive number become a negative number, and all kinds of goofy stuff can happen. And we'll see plenty of examples of that when we look at arithmetic. So that is what I want to cover for today. And we'll cover the other arithmetic operations on Tuesday. So thank you very much.